Good afternoon. My name is Zach Lick. I'm a third year grad student in David Sherrill's group, and I'm going to give you a brief overview of the symmetry adapted perturbation theory, or SAPT code, that's in Psi4, and how to run it. Before we actually get into running the code, I'll start with an overview of what SAPT is. Put briefly, SAPT is a method that calculates non-covalent interactions. Calculating non-covalent interactions, and doing so with quantitative accuracy, which is possible with SAPT, is something that's really important if the problems that you work on are, say, how molecular crystals pack and what their crystal lattice energies are, or maybe how exactly ligands bind to proteins, both of which are problems that we've tackled with the SAPT code in Psi4. Getting a little more specific here, the SAPT code in Psi4 is for calculating two-body or dimer interaction energies. SAPT is not the only way to go about calculating dimer interaction energies, but it has some unique advantages over the standard supermolecular approach. So first let me describe what the supermolecular approach is, and then we'll contrast it with SAPT. For the supermolecular approach, say we have a single molecule, benzene. We can use any quantum chemistry method, in this case a high-level coupled cluster, and calculate the electronic energy of benzene, which is about negative 232 Hartrees. Then we can form a dimer from two copies of the same benzene monomer. Here this is the sandwich benzene geometry. The energy of the dimer with the same coupled cluster method is about double the monomer energy, but not quite. In this case, it's a little more than double. From these two numbers, we can then work out an interaction energy as the dimer energy minus each of the monomer energies. This is what we call a supermolecular interaction energy, which you can get with any quantum chemistry method, but there are a couple downsides to this. So note that the actual monomer and dimer energies are on the order of hundreds of Hartrees, whereas the interaction energy is only a couple milli-Hartree. This means that to get an accurate interaction energy, you're going to heavily rely on error cancellation between the dimer and monomer energies, and this is something that SAPT avoids. So how exactly does SAPT work? SAPT is a perturbation theory, and in this perturbation theory, we try to describe the total dimer Hamiltonian, starting with a first-order Hamiltonian that is just a Hartree-Fock description of each monomer independent of the other monomer. So in other words, we solve Hartree-Fock for monomer A and we solve Hartree-Fock for monomer B. On top of that, the perturbation is the intramonomer correlation of each monomer, again, independent of the other monomer. So this right here so far is just equivalent to doing molar-Plesset perturbation theory on each monomer. Added to that, however, then we tack on the intermonomer interaction, which is the electrons and nuclei of one monomer interacting with the electrons and nuclei of the other. When we go about actually solving this perturbation series, and by the way, this review I have in the bottom left, Konrad Patkowski, it just came out this past year, is a really excellent resource on all of this, the derivation of SAPT and all the different terms. So anyway, when we go about solving this perturbation series, we get a total SAPT interaction energy. And because it's a perturbation series, and specifically a double perturbation series, we get many different terms to form the total interaction energy, indexed here by M and N, the order in the inter and intra perturbation series. From here is where the real utility of SAPT comes about. So we have all of these terms, and by examining them, we can find that the individual terms correspond to physically meaningful types of intermolecular interactions. So we can group them into these four categories, each of which corresponds to something you would have seen in a general chemistry class. We have terms corresponding to electrostatic interactions, exchange or steric repulsion interactions, induction or polarization interactions, and then lastly, London dispersion forces. So not only do we get a SAPT interaction energy, but we can write that interaction energy in terms of four physically meaningful components, and know not only how strong an interaction energy is, but why it is that strength. This is one of the main draws of SAPT. So like I said, we have this double perturbation series, and generally the higher order terms are much more expensive to compute than the lower order terms, and those higher order terms also hopefully are much smaller in magnitude, meaning the series converges and they're less important. Because of this, we have many different what we call levels of SAPT based on the truncation in the perturbation series. This is just like you have in molar-Plesset perturbation theory or coupled cluster theory. You have different kinds of the same method. The most common SAPT is probably SAPT0, where we don't have any intramonomer correlation, but we have a second-order intermolecular interaction. The SAPT code in Psi4 can handle up to maybe 300 atoms with a modest double zeta basis set and gets pretty accurate results with the right basis set, as described in this paper at the bottom, Trent Parker 2014. We can add in some of the intramonomer correlation to get higher levels of SAPT, like SAPT2 and SAPT2+, and then even add some more intermonomer interaction to get the SAPT2 plus parenthesis 3 and 2 plus 3. So this sort of describes the set of different SAPT methods that we have available in Psi4, increasing in both accuracy and cost. And with that, let's actually run some SAPT calculations in Psi4. So to start out, we'll run a SAPT0 job on the hydrogen bonded water dimer, which is a pretty simple system. It's very small, so the calculation will run fast. And we know this interaction very well. It's a hydrogen bond, which is a very strong electrostatic interaction. So I'll go over to my terminal and first get the geometry of the hydrogen dimer. So I have that here in Cartesian coordinates. It's 6 atoms. The coordinates are all in angstroms. And I'll also open up a template input file that's been half written. So this is a Psi4 input file. First, I specify the memory. My machine has 64 gigabytes. I'll give it 60 to avoid overflow, even though this job needs nowhere near that much. I define the molecule and its geometry. I select a basis set, June CCPVDZ, and then finally have an energy call here, where I also tell Psi4 what molecule to use. Telling Psi4 the molecule here is optional because there's only one, so it'll default to the last active molecule, which will be this H2O dimer. So let me copy this geometry and place it here in this molecule block. A very important note in running these SAPT calculations is you have to manually specify your two monomers, the two fragments. And you do that in Psi4 with these two hyphens. So Psi4 can't automatically know that this is a dimer and not one single monomer. On top of this, I'm going to go ahead and tell Psi4 that each of these waters has a neutral charge and is a singlet, although that is the default assumption. So that's optional, but still a good practice. Okay, so let's close out of these. We'll run with 6 cores this input file that we just wrote. It's a pretty simple input file, so it should only take a second, and it's already done. Oops. All right, so here's the input file. Starting at the top, we see a header. Sorry, here's the output file. Our input file is reproduced for us. Next, we'll see the Hartree-Fock jobs that I ran on each monomer. Psi4 will actually also run a dimer Hartree-Fock, so we can get some supermolecular terms. So there's the dimer Hartree-Fock, the monomer A Hartree-Fock, the monomer B Hartree-Fock, And then finally we get to the SAPT0 part, which is pretty short. Whenever you have one of these SAPT output files, all you really need is this table that's printed at the very end, right before the final timing information. So we see we're given our 4 components: electrostatics, exchange, induction, and dispersion. We have them in a few different energy units, and we also have underneath them some of the individual terms and scaling factors and other pieces of information that go into the total grouping of that component. So in this case, the electrostatics energy is negative 8.8 kcals per mole. That's very strong. The exchange is almost equally repulsive. So exchange is always going to be a repulsive term. Electrostatics can be repulsive or attractive, depending on the individual dimer. And then these last 2 terms, induction and dispersion, tend to be smaller than electrostatics and exchange, but they're always attractive, so they're going to be negative. Down here we see our total SAPT0 energy, negative 5.08 kcals per mole. A misconception you might have is that the SAPT0 energy should be the same as the Hartree-Fock energy, since both of these don't have intramonomer correlation, but SAPT0 is a very different method than Hartree-Fock because it does have the intermonomer dispersion that Hartree-Fock's missing. So SAPT0 will always be a more negative and attractive number. And this is it, the basics of running a SAPT0 job in Psi4. I'll quit out of this file and show you that we can also pretty easily run a SAPT2+3 job without much change. So here's the same input file. Now we've changed the call right here from SAPT0 to SAPT2+3, and this system is small enough that even SAPT2+3, which is the most expensive SAPT, will also run really fast. So let's look at this output file and see how it's different. So I won't scroll up to the Hartree-Fock part, that's all the same. All we really need is this table at the end. We'll see that we still have our 4 components: electrostatics, exchange, induction, dispersion, though the numbers are a little bit different. And underneath each we have extra information because there are more terms, since this is a later truncation. Also note that because all of the SAPT methods are cumulative, so the earlier SAPT methods are just subsets of the later SAPT method, we not only get the SAPT2+3, but we can go ahead and just calculate what the SAPT0 interaction energy would have been because we have all those terms. So here we can see that with the SAPT2+3 method, the total interaction energy is about negative 4.18 kcals per mole, which is pretty different than SAPT0. And it sort of looks like SAPT0 kind of misses this energy, but all of these later terms agree on it, or all of these later levels agree on it. All right, that is all for SAPT2+3. One other thing that I'd like to point out is that the way that we've been running these Psi4 jobs is just one of the few different ways that you can run Psi4 calculations. So let me go back to this SAPT2+3 input we have. This format is what we call Python. So it's a Psi4 input file, and we run it with Psi4 as an executable, but we can put some Python-like syntax in there. I'll show you a completely equivalent input file that you instead would run with an actual Python executable. So on the left, I have what we call the Psi API format. You here import Psi4 as an actual Python module, and everything that we did on the right in Python, we can do something equivalent on the left with that Python module. The difference between these two comes down to personal preference. I prefer the one on the right when I'm doing a one-off calculation, and the one on the left when I'm doing a lot of file manipulation or working with part of a bigger code base or project. The reason I wanted to show you this, however, is to show you how easy it is to go from something on the left, which is just a simple Python Psi4 calculation, to a more complicated project that might resemble something more like a research project. So let me open this other file that I've already written. Oops. There we go. Okay, so this is pretty simple, or similar to the previous Psi4 water dimer calculation that we just saw. We import Psi4, a few other things, set some output files, memory, number of threads, basis set, and then just here have the SAPT calculation abstracted, where we give it a molecule, it runs SAPT2, and then returns our total energy in 4 components in the units of kcals per mole. So now that we've defined this run SAPT function right here, we can go to the Python main function and define a list of distances, get the benzene dimer that we looked at earlier in that slide deck, and at each distance, create a benzene molecule where the separation between the benzenes is that distance. And then we'll append them to a list, print out some information, before that, run SAPT on the benzene dimer, append the energies to a list, print out information, and then at the very end, graph it. So I will exit out of this file. Running this takes maybe 30 minutes, so I obviously won't do that. But I will show you that final output, the graph that it makes. It looks something like this. So we see for that benzene sandwich dimer, in fact, I'll go back to the geometry in case you've forgotten what it looks like. Here it is. If we pull the benzenes apart, the interaction here in black goes from about negative 1.8 or 1.9 kcals per mole all the way down to 0. Additionally, we can look along this reaction coordinate at the 4 different SAPT components and how they factor into it. So we see exchange is obviously really repulsive and gets repulsive at short distances. Here, dispersion is the most stabilizing force instead of the electrostatics we saw in the water dimer example. And we actually see that the electrostatics force becomes repulsive along this coordinate. Induction doesn't really have much of an effect. So part of the reason I'm showing you this is because this result was a graph that came out of that same benzene dimer paper where I got the geometry from. And it's that easy to take some experimental result like this, or some computational result, and reproduce it in Psi4 with just a simple Python input. All right, and with that, I think I will go back to this slide deck and just point out that this isn't even all of the SAPT capabilities in Psi4. We have some other methods, including a functional group SAPT, where not only do you get the SAPT components describing the interaction energies of a monomer, but you can localize those energies to different functional groups. So here, this is a phenyl dimer, and you can, in this visualization, see that the interaction between the hydroxyl and the rest of this monomer might be different than the aryl ring right here. Psi4 also has an intramolecular SAPT0, where you can calculate interactions between 2 different groups that may actually be covalently bound through some third linker. So if these are monomers A and B, this is C, which may covalently link them. And C does not have to covalently link them, which means that you can use this ISAP to also study solvent effects. We have a SAPT0 code for open shell systems. And we also have very recently a SAPT DFT, where if you think back to the perturbation theory setup, the Hartree-Fock zeroth order Hamiltonian is instead replaced by a cone-sham Hamiltonian, and that has a lot of other benefits that the Hartree-Fock doesn't, and has been shown to converge to a more accurate interaction energy a lot faster. So I'll end on this note. Here are some useful resources to getting started with SAPT and Psi4. There are a couple manual pages that detail all the SAPT code, and then the FI SAPT code in particular. I didn't focus on this FI SAPT very much because it is so well documented here. The Psi4 GitHub has a lot of sample input files, and if you just search in there for anything that has SAPT in it, you'll be able to find a lot of useful stuff. And then lastly, I'll put the few files I had in this presentation up on GitHub right here. All right, thank you for listening.